All right, well, welcome. Sorry we're a little bit delayed in getting started as we transition between presenters, but we're excited you're here this morning. My name is Jake Beers. I'm the Elementary Science Tosa here for Springdale Public Schools.
And I'm Jenny Gamble, and I am the K-5 STEM Specialist at the Northwest Arkansas Education Service Cooperative.
It's quite the mouthful.
Yes, it is.
So we're excited today. We're going to be talking about writing scientific explanations using the CER Framework. And this is something that's scalable, kindergarten up through 7th grade, something that a nice tool for any teacher to have in their toolbox as they're working on in science. So we're actually going to start with a video. So we're going to start off with a short little clip, and we'll jump in right after that.
I have evidence that proves my dad's a space alien. He speaks a weird language. He drinks green stuff. He says he's from Albuquerque. I'm not buying it. I mean, just look at him. And one more thing, he has a spaceship. The evidence doesn't lie. My dad's an alien.
The highly advanced Audi A6, named to car and drivers 10 best.
All right, well, she was pretty convinced in her explanation that her dad was a space alien. I heard her say things like, claim. She made a claim.
Yes.
And then she backed it up with some evidence, didn't she?
She did.
And so when we think about scientific explanations, we like to think about students constructing an explanation using those claims and evidence. Let's see if I can click over. And so a scientific explanation answers a question. It works to answer questions to explain how the natural world works. And so we call that phenomena, and you'll hear a lot of it's a current buzzword of phenomena, right? We hear it a lot, and we look at scientific texts, but explaining how the world works, whether it's the sun moving across the sky, things falling to the earth through gravity, just trying to explain that is what we're looking for in scientific explanations. And you know, Jake, we've been doing scientific explanations for years, and they've been in the standards that we had before the ones that we're using now, so just the Arkansas Science Standards, but the language of the new standards has really brought to light the need to focus on scientific explanations and to get kids doing them. I think that's a great point, because I think by practicing this skill, kids are really beginning to be able to articulate their understanding in science, and that's really powerful. So we're going to spend just a moment talking about why scientific explanations are important. And so, you know, one of the goals of science is to have the best explanation for a natural phenomena that is supported by the most evidence. So we want kids to be able to look at what's happening in the world and then have evidence to back that up. And that's what science has been doing for years, but again, it's going back to the student being able to explain why it's important. We also know that explanations are important because they're real life. It happens in every area of life, even in commercials. And so with science, it's a social process where scientists are debating claims and then refining and revising those claims based on evidence. It's happening every day in the scientific community. And I think that's authentic too. So like when science is not just a set of facts, right? So science explanations are constantly evolving, and so I think that's an important piece to teach kids, that science develops over time through conversations with scientists. And then another reason why they're important is that they help us make sense of science. You know, this really goes along with this 5E, where kids are the 5 E's of science, where kids are actively engaging in science. Again, you know, kids have to do science in order to understand science, and so that's where the active creation is taking place. And then perspective-wise, this is an opportunity for kids to compare their own explanations with other kids. And so you can see misconceptions that students have. They're learning from the thinking of other students, and I think this really is powerful for your ESL population. Yeah, I think it allows opportunities for structured student talk, for students to be engaged in conversation, just like we do in math, being able to collaborate in similar ways that we do in math. And then finally, the explanations are important because they foster 21st century skills, for example, analysis, evaluation, justification, reasoning, critiquing, argument, and then it engages students in the practices of science, the science and engineering practices. So this is STEM. You know, we think STEM is innovation, and it is engineering, it's all of that, but this is STEM learning where kids are really having to do what they're going to have to do in the world that they face after their K12 educational experience. You want to say any more about that?
I think we're good.
Okay.
So we're going to use this framework today. We're going to introduce you to this framework, the CER framework. And this framework isn't original to this book, but a lot of the work that we based our work on was from this book, What's Your Evidence? It's a great text as you're working to understand how the CER framework works and the background behind it. I highly recommend this text, and we have opportunities in our district. If that's a text you're interested in, we can look to get you that book as well. So just know that this comes from this book. It's a phenomenal book if you want to dive a little bit deeper into the CERs. So when we look at writing explanation, there's going to be 3 parts we're going to look at today. So when we write a scientific explanation, first we're going to have a claim. And so a claim is going to be the statement that answers our question. So it's going to be usually a 1 sentence. It's going to answers our question. It's not going to use the yes or no, and it could describe the relationships there. So just a simple 1-sentence claim is an important piece of that.
And Jake, just a second before you switch slides, something that he and I discussed about this being an investigation. The CER framework is often used with some sort of hands-on investigation, but it doesn't have to be used for that, and we'll get into that a little bit more. But just an investigation can be as simple as observations that you're making as you go on a sound walk.
Yeah, exactly. So we're going to look at some of that as we jump in today. So then evidence are what we use to support the claim. And so if you think back to our video of the little girl, she made a claim, I think my dad is a space alien, right? And then she made that claim, and then she had to back it up with evidence. And so he drinks weird things, he dresses funny in his bike outfit, and then the big one was that he had a spaceship, right? And so we looked at that Audi commercial as a student providing that claim and then backing it up with evidence. And then finally, we use reasoning to bring together the claim and the evidence. And this is where you bring in the scientific principles that students are learning through the lesson. And this is the piece that we usually add in upper grades. So in a K2 CER, we may just have the claim and the evidence and not incorporate the reasoning.
And I will say that this is probably the component that has been missing, that we've been doing this claims and evidence, although we haven't been using this framework. We did this with the previous Arkansas Science Standards, but we didn't take it to the next level with the reasoning component and bringing in the scientific principles that connect the claim and the evidence together.
Yeah. So we're going to model what this could look like through a simple investigation. So I brought with me this robot. We actually do something similar to this in 3rd grade. And so this robot, he actually is a wind-up toy. And so we're going to look at how we could use this wind-up toy to investigate forces in motion. And so our question we're going to look at and investigate today is, how does the number of times you wind up the toy affect the distance it travels? And so to do that, we'd wind them up in different amounts. And so here's the student investigation sheet where they're going to wind it up in different number of times, and they're going to predict and then collect some actual data. And so when we did this, we found that with 1 wind, we got 8 centimeters, 2 winds, 13 centimeters, 3 winds, 16, 4 winds, 22. And you can see that we have a presentation there.
And just so you know, we do realize that the units are missing. So all you math people out there, the units were not included on this.
Yeah, good point. And we'll note, and we can see that that does affect the way it travels, right? And so I feel like a lot of times this is where we typically leave it in a science classroom. We would have kids look at their data and maybe write a 1-sentence answer to the results.
If we even looked at the data, because that's something that often gets, I mean, we would look at the data, but really diving in deeper to it, that often gets overlooked.
And I know for me, usually I was always in a hurry to get into as many activities as I could, and so I was always, I would push this off to the side, and I would say, well, kids are going to probably come up with an answer on their own. They figured it out because they can see that it does affect it. But by actually having kids do some writing around it, man, it really helps us to bring to light their thinking.
And that's why, you know, we do have fewer standards, and it gives us an opportunity to do work like this around the learning that students are doing.
Yeah. So when we look at that claim, evidence, and reasoning framework we just introduced, we can look at how we can make our claim and evidence. So our question, remember, was how does the number of times you wind up a toy affect the distance it travels? And then our claim, remember, it's a one-sentence phrase. The more times you wind up the toy, the further the distance it will travel. So it doesn't have yes or no. It really answers that question. And then we backed it up with our evidence. And remember, this evidence can be things you observe, it can be things you record, and it provides you an opportunity to go and back up the claim you made. And we do this a lot in writing. If you think about opinion writing, we make a claim in opinion writing, we back it up with evidence. In math, we have an answer and we justify it. So this is a very transferable connection that kids can make. So in K2, K3, you may not incorporate the reasoning part. You may just stop right there. But when we think about reasoning, we gather our reasoning from usually a nonfiction text or discussions we have in the class. And so in this example, we would go to maybe a book like this, Making Machines with Springs, and we would use this nonfiction text or videos or classroom discussion to help provide some information that students can use in the reasoning component. And so say they read these pages about clock springs and storing up energy. As you wind this toy tighter, the spring gets tighter, it stores more energy. Students can then incorporate that information into their CER to fully flesh out their thinking. And so if we look back at this CER, we could have our claim and evidence from before, and then we would add our reasoning. So the toy robot was powered by a spring. Springs are made of a material which can store energy. And so connecting it to the science content just helps their students' CER or their reasoning go deeper.
And just, looking at that reasoning statement, that's a pretty intense reasoning statement, and your students are going to struggle with this. This CER is something that you are going to have to model for your students multiple times. You're going to have to do it whole class, but we see just the power in doing this work. And as Jake said, if they're doing it here, it's going to transfer over to math. It's going to transfer over to ELA. So it is spending time on this, you're going to get a lot of return on your investment.
I'd agree. And a lot of this, like you said, doing it whole group on a big chart paper and bringing their evidence together and debating and discussing and having those conversations using that structured student talk is a powerful way to incorporate some of the language frames that we already have embedded.
And again, the book itself says most likely kids in K1 and even second grade will stop with the claim and the evidence, and then the reasoning piece is end of second grade on up.
So we're going to look through a couple examples. I know we've been kind of moving kind of quickly, but we're going to stop and just look at a couple examples. And so here's the one in first grade. So what happens when an object makes a sound? The object vibrates when it makes a sound, and then they provide evidence. We saw the tuning forks move back and forth. We put water in the sound bowl and it vibrated. When we hit the bowl, we saw rice jumping from the vibrations on a drum. And notice that the evidence for this incorporates multiple investigations. And so when we looked at the robot, it was just one investigation that we used to collect our data. But many times a CER can be developed over the course of an entire unit.
Exactly.
And so it may not just be this one investigation we have to do a CER. That investigation may provide information that lends itself to a greater understanding of the concept that kids can then develop over time. We look at another example from 5th grade. This one's about shadows. So the question we're investigating is, what directions do shadows move throughout the day? And so our claim is that shadows change throughout the day by being long and thin in the morning, then short in the middle of the day, and longer in the afternoon. And so then we provide specific evidence. And even in this example, we just provided a claim and evidence with no reasoning. Because remember, that reasoning piece can be added later or developed over time as students learn more throughout the unit.
And again, Jake, back in the first grade and this one, notice the language there. It's we. The kids actually saw this. They were actively engaging in the content. We saw the tuning forks move back and forth. We looked at the shadows. So kids are doing science with CER.
Yeah. All right, so we're going to investigate, and we're going to unfortunately, you're not here. We wish you were here because this training is so much better when you're live and in person. But we're going to investigate together, and so we're going to do that through looking at a question about magnets, and we're going to do some modeling of this, and then you're going to take the data we collect, and we're going to begin to, you're going to write a CER on a Padlet, and so we'll share that with you in a few minutes. So if you don't have your computer around, make sure you maybe grab a computer. This can be something you do with a group of people if you're there together, or if you're by yourself, you can look at that as well. So we're going to collect data to investigate this question: are magnets attracted to all metals? And so this is officially in 2nd grade. We could look at this question in our new standards, or in 3rd. And so we're going to investigate today. So we like to start with prompts or probes. And so this one says, Jose says his magnet is attracted to anything made of metal. Mary disagreed. She says not all magnets are attracted to metals. So our thought is, who is correct? And we have to support our claim with evidence. And so we're going to conduct this investigation, and we're going to conduct it right here. It's going to be kind of hard to see, but we'll kind of go through this chart. And so our thought is, as we gather data through our investigation, we're going to then provide that for students to then make their claim and support the evidence. And so
let's have them just take a minute right now. You're looking at this list of items and make a quick prediction about these different items, whether or not you think they are magnetic or non-magnetic.
And they are all metal, so that's an important thing to remember, that all these are metal.
So we'll give you 2 minutes to do that right now.
All right, so you had a chance to maybe make some predictions, talk with people around you. And again, I want to go back and highlight that the question you choose to investigate is critical. So not every question is good for CER, and so having a good question is really important. So we're going to go through these materials real quickly, and we're going to decide, are they magnetic or non-magnetic? And so the first material we're going to test is a nail. And so our nail, I'm going to pick it up. Our nail is magnetic. All right, okay. We have a winner. All right, I'm going to sort this in 2 piles. Our nail is magnetic. Our next is a paper clip. Our paper clip is magnetic. Next one is steel wool. All right.
Steel
wool is magnetic.
Okay.
An empty soda can is non-magnetic.
Okay.
So that one's in a no pile. The next one's a thumbtack. Thumbtack is magnetic. Next one is a nickel.
No.
Nickel is non-magnetic. I'm going to put it on this side.
Okay.
We have a water bottle. I feel a little bit of magnetic attraction. It's hard, I can't pick it up. I think I'm going to go with...
same.
Yeah, same. You feel a little bit there. So I think it's magnetic.
Okay.
Key. Key is non-magnetic.
Okay.
And then a spoon is magnetic.
Perfect.
So we got 5 items that are magnetic.
Actually,
and 3,
we have 6 items that are magnetic.
You're right, my counting. And then 3 that are non, though they're all made of metal. And so we're going to watch this little video clip. to take a look at providing some reasoning. So we have some evidence that we collected, and now what we're going to do is watch this short little minute-long video clip to see if we can gain some understanding or some reasoning behind why things may be magnetic or non-magnetic.
And iron, anything containing those three metals was magnetic.
And I think that's important. We could have showed that video before, right? But that would have taken away a lot of the mystery, a lot of the fun of exploring. But that video provides an opportunity to connect to the reasoning. Because without that video, we obviously have things that we've identified that there is something going on with some metals that are magnetic and some that are not. But without having some reasoning, without having some information from an outside source, it's hard for kids to be able to identify that component. So what we're going to do is we're going to provide you some time to actually write a claim and evidence statement about this investigation. And so if you go to tinyurl.com/CER and then Sdale, all in one, it's going to take you to this Padlet right here. And when you get the Padlet, you just double click on the Padlet, and you're going to write a CER statement for this magnetic investigation. Are magnets attracted to all metals? And so you'll have two things. You'll have a claim, and then you're going to back it up with evidence. And your evidence is going to be from the investigation we did here. If you want to extend your thinking and provide the reasoning that we saw from the video, you're welcome to. But in this thing, you're going to just do the claim and the evidence component. I think we'll give you about 7 minutes, 5 to 7 minutes to do that. And we'll then jump in there and we'll check and see what are some of the claims and evidence that our teachers wrote. And then we'll look at one that we came up with for this. And then we'll wrap up by looking at where they are in our standards and how this connects to ACT Aspire.
And we're going to remind you again, take them back to that chart so they can just see the items that we tested again.
Oh, yeah.
So remember, 6 of those were the non-magnetic ones, were the empty soda can, the nickel, and the key. The key.
Yep.
Yes. Okay.
So we'll give you about 5 minutes to start, and then we'll jump on over, and then we'll come back from there.
we're ready.
Are we ready?
Yep.
Well, welcome back. Y'all worked hard to fill this page, which is phenomenal. And I think Jay and I were talking that Padlets are such an easy tool to provide a space for students to easily projectile responses. And then as a class, you can go through and look at all the different CERs that people constructed and went through.
Yeah, and it's a really safe space for kids to do it because they're not having to say it publicly, and it's giving every student an opportunity to have a voice.
And I think what's great about, as you go through these, there's an opportunity for, man, look at all of the data collected that students have collected and gone through. So again, as we look across these, a lot of people did a great job of identifying they wrote claim. That's something that if you're initially teaching, would it actually be a good thing to work with kids on, is maybe saying, writing the word claim and making sure they have a claim, but you don't have to. Some people started with some metals are and some metals are not attracted to magnets. So answering the question is critical as you go through that.
And what we're seeing, what I'm seeing in some of these anyway, is that there's a little bit of the reasoning piece that's mixed in with the evidence statement, and which is okay, but in your evidence statement, you really only had to say which of the items were magnetic and which of the items were non-magnetic, or even just 4 of the 6 items were magnetic, or I'm sorry, I think we did 9, but 6 of the 9 were magnetic and 3 were non-magnetic. And then you could have saved, like you're going to see on our next slide when we get to it, that the reasoning piece really brings in the idea of the nickel, iron, and cobalt being attracted to magnets.
Exactly. So overall, y'all did a fantastic job. Way to go.
And I love just the differences in the way that they wrote these out. This is great. So we're going to transition back then to the PowerPoint and look at a simple CER that we did for this investigation together.
And again, this is not a perfect one. I think there were great examples that we all came up with. So our claim is magnets are not attracted to all metals. So remember, going right back and answering the question with a claim. And so even having kids reframe parts of the question is a good strategy that we can work on.
Yeah, like the restate the question, something that you do in ELA, that's what we did basically there.
But you don't always have to do that, because sometimes your claim may not be exactly, it may not match. But so ours was magnets are not attracted to all metals, and then we provided our evidence, like y'all did in your examples, and then we pulled out the reasoning at the bottom. Magnets are attracted to metals that contain the minerals iron, nickel, and cobalt. Not all metals contain these minerals. And so connecting it back to the video, and again, you may not do this in one class period. This may be over the course of a week that you are gaining this evidence. It may be the reasoning is embedded throughout the reading, the discussion, the conversations that kids have is where they're going to pull in that reasoning component.
And if you're doing this on a chart and not doing, not using technology, you can make your claim and evidence. You can set up a CER on, just a 3. Well, if you go something that's similar to this, and then have kids do it on Post-it notes
and stick it right to it.
Yeah.
Yeah. So they can write their claim. They could add their evidence as they go. So we're going to look at how these are embedded, more the application piece now. So we spent about half our time talking about what is a CER and a scientific explanation, and now we're going to spend the last about 10 minutes talking about how they're embedded into our standards. And so when we look at our new K12 Science, Arkansas K12 Science Standards, we'll see that the language in our standards has construct an argument supported by evidence, or make observations to construct an argument based on evidence. Make observations to construct evidence-based accounts. And so you'll see that this language of evidence-based, constructing evidence-based accounts or arguments requires students to use the evidence they're collecting and then making a claim.
And this correlates directly to this one particular science and engineering practice to engage in argument from evidence. Kids can't anymore just make a claim and make something up. If they even make it, we do the claim all the time, but we don't often bring in the evidence, and it's not scientific. And so this is where we're really wanting kids to develop this skill. And notice again that you're going to see this is K7, it's actually K12, and kids are going to get better at this over time. But it starts in kindergarten.
It does. You'll see even in kindergarten we're looking at evidence about plants and animals change their environment. We go up to 3rd grade. There's tons of these in 3rd grade. And Jenny and I were also talking that even if the standard doesn't say construct an explanation, maybe it's plan and investigation, students are still going to be having to do some sort of scientific explanation based on that. So just know that those are the 4th grade ones, the 5th grade ones. These are in every single grade level that we're using CERs. And as Jenny mentioned before, in K2 we may be doing a whole group, just doing the C and the E. In 3rd, 4th, and 5th, we begin to hopefully develop more independence and adding the reasoning component. But man, starting this practice early of incorporating good scientific reasoning is really powerful.
And then I think, like we said, the return that you're going to get on your investment of time in doing this is going to show up in other subject areas.
I totally agree. So, ICT Aspire is coming up, and that's a big part of our work that we're doing with our kids. And science now counts for about 7.5% of your overall score. And so it is important that students are aware of how to answer a science investigation. And so here's an example from 3rd grade. It's about clouds. And so students are given this big data table, and then they have to answer this question. Students saw bright flashes of lightning in the sky. Based on the table, which type of cloud most likely produced the lightning? Explain your answer using information from the table. Well, if you look at that question, that is perfect for a claim and evidence, right? And so to do that, students have to look at the chart, and they'll notice that it's the cumulonimbus cloud, right? That's a mouthful.
That is a mouthful.
And that's the only one in the chart that produces lightning, and they have to back their evidence is by looking at the chart and being able to provide that explanation.
And they needed to know nothing about clouds. They only needed to know how to read the data from the chart to make a claim about that data and use evidence from the chart to explain their answer.
Yeah, because when we look at the ACT Aspire, you're not going to get just one type of content. You're going to get content from all the sciences. And so being able to dive into any content and use a claim and an evidence is really powerful. There's tons of resources out for CER, and just a quick Google search will get you tons of different resources as well. We wanted to provide a couple. This is a good, Beth Pesnell from Rogers and I did a lot of CER training, and she developed this for, this is like a K2 version where students are writing the question, they have their notes and their research, and then they can write their claim and their evidence. And so again, this would be more independent K2 practice. Same thing for 3 through 5. What's your claim, what's your evidence, and what's your reasoning? Again, these pages just provide a framework. Man, students can do this on Padlet. They can do it on a Google Doc. They can do it on just notebook paper. It doesn't always have to be on this paper like this.
And especially in the lower grades, but even for your ESLs, you can scaffold this for them by having them make their evidence from drawings. Mm-hmm. And so they do those drawings and then they write their evidence statement, trying to bring in some of that language where they've maybe added some details with just short phrases or words. Mm-hmm. But like we said, your kids aren't going to be ready for this all at once. It's going to take some scaffolding, some modeling, whole group practice.
Yeah, and there are language supports that have been developed for claim and evidence from here in Springdale, and so those are available in the units as well. One of the things that I think is a great way to work with kids is to color code their responses. And so as you go back into any claim and evidence, as you write them, you can use the blue, orange, and green. So here's an example of one I wrote for a sealed bag of air, where I wrote my claim in blue, my evidence in orange, and my reasoning in green. It just helps to highlight the different components of that. And so this is it's just a simple scaffold you can do. You can also have students go back and underline the claim, evidence, and reasoning. You can even have them do that with trade with another group and see if they can identify the other group's claim, evidence, and reasoning. So it's just another simple visual strategy to help students. The teaching channel has phenomenal claim, evidence, and reasoning videos in real life practice. And so here's an example of that. Again, there's just good videos out there that highlight this practice that are short, 5 to 10 minutes long. They just show it in the real world.
And with this particular example here, it's a series of 3 videos, and it looks at a CER from the beginning stages of planning to use it in her lesson, then actually doing it with her kids, and then reflecting on what she got out of it. So this example specifically is a great one to watch.
And in our units, there's multiple opportunities to incorporate CER. I mean, the goal is that they're embedded into our curriculum already, that there's places to do a claims and evidence statement. But again, any investigation that you're doing is an opportunity to do a claim and evidence. And so we want to just wrap up by kind of doing some quick mental brainstorming as a team or individually. How will you engage your students in constructing explanations? Are you doing something this week coming up where you can incorporate the claim and evidence and reasoning component? As you think about your content, where in your content would this be a good place to fit? Are there testable questions that you're coming up with that you can investigate? And then what would that investigation look like as you're going through? And so, as you're thinking about CER and you're thinking about claims and evidence, know that, again, that they're embedded into our curriculum as much as we possibly can. But there are tons of opportunities as a teacher to incorporate them further into your thinking, students' thinking. Anything else?
I would just say give it a try. If your kids don't do a great job with it the first time around, keep at it. This is something that is going to be developed over time. And so, ideally you would start this at the beginning of the year, and we're already in the month of February, but I don't think it's too late to do it now. And if you're doing it now with your students, then, the teacher, the grade level that they move up to next, she's going to be able to build on that, and so on. And so, it'd be so cool to see kids starting this in kindergarten in Springdale schools, and then by the time they get to 5th grade, they can just roll these out.
Yeah, I agree. Well, we're excited to be able to plan. We really believe that the CER framework and having students engage in arguments from evidence is a powerful component of science instruction. And know that we're both here to support teachers in Springdale. And so, my email is jbeers@sdale.org. We got Jenny's up on the screen as well. And just know that we're here to support you guys as we go forward. If you do have any questions, please feel free to reach out. We hope you guys have a great rest of your day.
Thanks.